On a quiet Wednesday night in March, an orbital analyst at NASA's Jet Propulsion Laboratory refreshed a tracking solution for a faint comet sliding through the inner solar system, and the residual plot refused to behave. The numbers should have tightened. Fresh observations from 3 separate telescopes, precise timing, clean reference stars. Everything that normally forces an orbital path to snap into sharper focus. Instead, the fit quality degraded. The tiny offsets between where 3I at last was predicted to be and where it actually appeared, those quiet errors astronomers call residuals, weren't shrinking. They were widening. Night after night, the object sat slightly elsewhere than physics said it should. This isn't the kind of anomaly that announces itself with a bright flash or a sudden change in the sky. It lives in spreadsheets, in chi-squared values that creep upward when they should fall, in position errors that grow from fractions of an arc-second to something uncomfortably larger, as if the comet is drifting away from its own predicted future. And the unsettling part isn't that the measurements are wrong, it's that they might be right. Because the astrometry is accurate, then something is pushing on 3I at last that the gravitational model doesn't account for. Or something about how we're measuring its position is being distorted in a way the reduction pipeline doesn't expect. And right now, the data won't let anyone confidently choose between those 2 possibilities. If you find yourself drawn into mysteries like this, where the strangeness lives not in spectacle, but in the stubborn refusal of numbers to align, subscribe now for more Beyond the Solar Veil cosmic investigations. The anomaly didn't begin with a telescope. It began with a flag inside the orbital determination system, an automated alert triggered when successive iterations of a solution fail to converge cleanly. Every night, as new astrometric measurements arrive from observatories scattered across 2 hemispheres, the software recomputes the object's trajectory, position, velocity, the subtle gravitational tugs from planets, radiation pressure from planets, sunlight, and if necessary, a term for non-gravitational acceleration. Under normal circumstances, adding high-quality data improves the fit. The computed orbit should wrap more tightly around the observed positions. Uncertainty ellipses should shrink. But with 3I at last, the opposite happened. After a certain date, roughly mid-March, as the comet descended past 1.3 astronomical units from the Sun, new observations started to pull away from the model. Not dramatically, not in a way visible to the human eye through an eyepiece, but decisively, in the language of astrometry, observed minus computed offsets, the OC residuals began to drift systematically in one direction. Analysts ran diagnostics. They suspected timing errors first. Exposure timestamps miscalibrated by a few seconds can masquerade as real motion. Then they checked the star catalog used for reference frame alignment. If the background stars themselves are slightly misplaced in the catalog, every measurement of the comet's position inherits that bias. They tested for trailing loss. When a comet moves fast relative to the stars during a long exposure, its light smears into a streak, and the centroid, the mathematical center of that streak, can shift depending on how the image is processed. They looked for evidence of a faint, unresolved coma that might be asymmetrically distributed, placing the brightest point of light slightly off-center from the nucleus itself. Each test narrowed the possibilities, but none eliminated the problem. Then someone tried something simple and disturbing. They removed the most recent week of observations and recomputed the orbit. The fit healed. The residuals collapsed back into the noise. Add those observations back in, and the orbit bends, subtly but persistently, as if the comet is being nudged. That's not an answer. It's a fork in the investigation. Either the newest measurements are contaminated by something the team hasn't identified yet, or 3, Atlas genuinely began behaving differently in mid-March, and the old gravitational model, the one that worked perfectly well in February, is no longer sufficient. The contradiction sharpens when you layer in the second kind of data: what the comet looks like. If outgassing were responsible for the orbital anomaly, jets of sublimating ice pushing asymmetrically on the nucleus, the most common explanation for non-gravitational acceleration, you'd expect correlated changes in the comet's appearance. Brightness surges, morphological shifts in the coma. asymmetries in dust distribution that track with the sun's illumination angle. Photometry should show variability tied to rotation and activity. Imaging should reveal subtle jets or fans emerging from specific regions of the nucleus. But 3I at last doesn't cooperate. Its brightness curve is smooth, almost boring. Observers report a faint, symmetric coma. Fuzzy, yes, but without the lopsided structure that screams active jetting. There are no sudden brightenings that correlate with the dates when the astrometric residuals worsen. No clear dust features. No spectroscopic detections of strong gas lines in the optical or near-infrared bands, where water vapor and CN radicals usually light up. This is where the mystery stops being a simple orbital puzzle and becomes something stranger. The photometry and the astrometry are telling two different stories, and both should be reflections of the same physical object. If the comet is quiet, if its appearance suggests low activity, then where is the push coming from? And if the push isn't real, if it's an artifact of measurement, then why does it appear so systematically, across multiple nights, multiple telescopes, multiple observers who use different reduction techniques? One possibility, quiet and destabilizing, is that the anomaly is geometric. The center of light, the brightest point in an image, the spot the astrometry software locks onto, might not be the center of mass. If 3I at last has an extended, optically thin dust cloud that shifts its distribution slightly as the viewing geometry changes, the photocenter could wander even if the nucleus itself follows a perfectly predictable path. Rotation matters here. Phase angle matters. The angle between the sun, the comet, and Earth changes every night. And with it, the way sunlight scatters off dust grains at different distances from the nucleus. A subtle change in coma asymmetry, too faint to show up as obvious structure in images, but enough to shift the centroid by 1/10 of an arcsecond, could mimic acceleration. It would look like motion. It would degrade the orbit fit. But it wouldn't be real thrust. It would be an illusion, written in light. The alternative is that the acceleration is real, and the lack of dramatic activity simply means the mechanism is different from what astronomers expect. Not every comet advertises its outgassing with bright jets and spectral fireworks. Some are dust-dominated, releasing fine particles without much gas to carry the signature emission lines. Others are driven by more volatile ices, carbon monoxide, carbon dioxide, that sublimate efficiently but don't produce the optical glows that water does. And some objects might be in a transitional state, heating up as they approach the sun, beginning to shed material, but not yet crossing the threshold where that mass loss becomes visually obvious. In such cases, the force is present before the spectacle arrives. The investigation tightens when you anchor it to distance. The anomaly doesn't appear randomly. It emerges, or intensifies, near a specific heliocentric range, between 1.5 and 1.2 astronomical units from the sun. This is not an arbitrary boundary. It's a regime where thermal physics changes rapidly. Water ice, dormant and stable beyond 2 AU, begins to sublimate with enough intensity to lift dust. Solar radiation pressure, already a factor for small grains, becomes more efficient as the dust-to-gas ratio shifts. If 3I, Atlas crossed a threshold, an invisible line where its surface temperature climbed past the point where a particular ice species transitions from solid to vapor, the onset of activity could happen faster than the observing cadence can cleanly resolve. Events that should follow a neat sequence, first heating, then measurable activity, then observable thrust, compress into a window of days, maybe weeks. And if the astrometric residuals start growing during that same window, the correlation is hard to ignore. But the timeline doesn't align cleanly. The brightening, if present at all, is too gradual. The spectroscopic searches for gas come back weak or null. The morphology stays stubborn. What should be a clear cause and effect relationship? Solar heating triggers outgassing. Outgassing produces visible activity. Activity explains the orbital perturbation. Fractures into ambiguity. The comet is behaving like something caught between two states, not quite inert, not quite active, existing in a narrow band where the physics is loud enough to matter but too quiet to measure directly. This leads to the missing signature. if a non-gravitational force is accelerating 3E Atlas. The simplest explanation is asymmetric mass loss. A jet, a hotspot, a localized source of vapor streaming preferentially in one direction. But the strongest tracers of that process are absent, or at least too faint to confirm decisively. Observers have looked for hydroxyl emission, the fingerprint of water vapor breaking down under sunlight. They've searched for CN bands, another common comet diagnostic. They've scanned in the near-infrared for signs of carbon dioxide. The detections, if they exist, are marginal, too weak to account for the magnitude of acceleration the orbit residuals suggest. That doesn't kill the outgassing hypothesis. It complicates it. Activity can hide. Dust can dominate. Co can drive jets without lighting up the wavelengths most commonly monitored. Geometry can cloak structure. A jet, aimed nearly toward or away from Earth, won't show up as a classic fan in images. And if the grains are large, tens to hundreds of microns, they don't scatter light efficiently in the optical, but they still carry momentum. They can still push. The alternative interpretation is that the force isn't primarily mass loss at all. It could be radiation pressure acting on an extended dust environment. If 3I Atlas is surrounded by a sparse cloud of small grains, and those grains are being pushed outward by sunlight faster than they fall back, the effective position of the comet, the brightness-weighted centroid observers measure, could shift relative to the nucleus's true center of mass. This wouldn't require strong outgassing. It wouldn't demand bright spectral lines. It would just require dust, sunlight, and time. And as the comet's distance from the sun changes, the radiation pressure efficiency changes. The grain dynamics change, and the centroid offset changes. That shifting offset, sampled night after night, would appear in the astrometry as a systematic error, a ghost motion, indistinguishable from real acceleration unless you can separate the nucleus from the coma. Multiple explanations survive, each internally consistent, each demanding a specific, testable consequence. The investigative tension is no longer what is 3I Atlas doing. It's which kind of uncertainty are we facing? Is this physics we haven't fully captured, or observation we haven't fully interpreted? The next decisive evidence will not be a dramatic image. It will be correlation. A pattern that links astrometric residuals to a measurable physical property. Rotation phase, viewing geometry, heliocentric distance, or photometric behavior. Find that correlation, and the degeneracy collapses. Miss it, and the comet slips away into the uncertain category of objects we can track, but not fully explain. So the question NASA faces now is not what happened. It's what measurement can break the tie? The answer is diagnostic, not exploratory. Compare astrometry solutions using different star catalogs. If the residuals shift when you switch reference frames, the problem is calibration. Examine the residual patterns for dependence on phase angle or seeing conditions. If the errors grow when the comet is observed at low elevation or poor transparency, the problem is atmospheric or centroiding bias. Search for photocenter shifts in multiband imaging. If the position of the comet's brightness peak moves between filters, the coma is chromatic and the centroid is geometry dependent. Coordinate observations from widely separated sites, measuring the same object at the same time from different vantage points. Parallax and timing differences can isolate systematic errors that wouldn't appear in single-site data. Higher leverage opportunities exist, though they require luck and coordination. Stellar occultations, events where 3I Atlas passes directly in front of a distant star, can constrain the size, shape, and opacity structure of the nucleus and inner coma independently of photometry. Multi-wavelength spectroscopy, especially in the thermal infrared, can distinguish between water-driven and code-driven activity. High-resolution imaging with adaptive optics or space-based telescopes can resolve the inner coma structure on scales of a few hundred kilometers, revealing jets too faint for ground-based wide-field surveys. Each observation narrows the probability tree. Each null result is almost as valuable as a detection because it rules out classes of explanations. The timeline matters. 3 Atlas is inbound approaching perihelion, the closest point in its orbit to the Sun, scheduled for late May. As it gets closer, solar heating intensifies. If the anomaly is thermal, it will strengthen. If it's geometry, the changing phase angle will modulate it. If it's outgassing onset, activity should become unambiguous in the coming weeks. But if the object's rotation and surface properties are inhomogeneous, if different hemispheres have different compositions, different thermal inertias, then predicting exactly when the behavior will change is harder. The uncertainty envelope, already uncomfortable, could widen. And for mission planners, orbital predictors, and long-term tracking systems, that widening uncertainty is the problem. Not drama, not danger, just the slow erosion of confidence in where, exactly, 3A Atlas will be 6 months from now. And so the investigation doesn't climax. It persists. Data continues to arrive. The residuals continue to evolve. Analysts continue to test, refine, and rule out. Somewhere between the astrometry and the photometry, between the models and the measurements, between what should happen and what is happening, the truth sits quietly, waiting to be resolved by a correlation, a pattern, or a single decisive observation that forces all the other possibilities to collapse. This is what 3I Atlas teaches, even if it never reveals its secret completely. Small objects can expose the edges of our models, our instruments, and our assumptions. The mystery isn't that we don't know what's happening. It's that we know just enough to realize we don't know which kind of uncertainty we're facing. Physics we haven't fully captured, or data we haven't fully interpreted. And that distinction matters because science doesn't advance by answering every question. It advances by learning to ask better ones. By admitting when the signal is real, but the explanation is incomplete. By resisting the urge to force conclusions when the evidence still holds multiple meanings. The orbital anomaly may resolve in the next month. It may persist for years. It may turn out to be a measurement artifact so subtle that only a new generation of astrometric instruments can finally isolate it. Or it may be real acceleration, driven by processes we understand in principle, but can't yet measure with the precision required to close the case. Either way, the comet will continue its journey, indifferent to the models we build around it, indifferent to the questions it leaves unanswered. And that's the point. The universe doesn't rush its explanations. It doesn't pause to reassure us. It simply is complex, ambiguous, beautifully resistant to easy interpretation. 3A Atlas, unremarkable in size, modest in brightness, will pass through the inner solar system and fade back into the dark, carrying with it a small, quiet reminder that even in the age of automated surveys and orbital determination pipelines, with telescopes on every continent and data pouring in every night, some objects still manage to sit just beyond the edge of what we can confidently say. And maybe that's not a failure. Maybe that's the frontier, where measurement meets mystery and the work continues.